Senior, let's go to the second type of electron configuration called the quantum electron configuration. Let's go. Number two now. Quantum. These are very simple stuff. Quantum electron configuration. Quantum electron configuration. Now, quantum electron configuration shows the arrangement of this shows the arrangement of what? This shows the arrangement of electrons in the subshells. Can you see the difference now? This shows the arrangement of electrons in the subshells and orbitals. This shows the arrangement of electrons in the subshells and orbitals of an atom. Quantum electron configuration shows the arrangement of electrons in the subshells and orbital of an atom. Now, let me do a small table. Shell configuration, then quantum configuration, so that you can see the difference at a glance. As you can see, I'll try to put this up. As you can see, let's just write one or two differences. What do we do in shell configuration? Arrangement of electrons in shells. I'm going to shorten it, of electrons in what? Shells. Then this one shows arrangement of electrons in subshells and what? Orbitals. So I've given you one difference. Let me leave enough space. It's your duty to at least find maybe 2 or 3 more. You can use your phone to do that. Just find like 2 or 3 more differences. Let's continue with our quantum electron configuration. Now, to write quantum electron configuration, there are rules. Rules for writing the quantum electron configuration of atoms. Rules for writing the quantum electron configuration of atoms. You can fill this up yourself. I'm trying to manage my time here. I don't have too much of it. So, rules for writing the quantum electron configuration of atoms. Let's take it one by one. The first one is called the AUFBAU principle. Second one is called HUND'S rule. For short, we call it HUND'S rule. Sometimes you find it written as HUND'S rule of maximum multiplicity. So that's the second rule for writing the quantum electron configuration of atoms. So used in describing the quantum electron configuration of atoms. The third one is called the Pauli exclusion principle. Alright, now let's take it one by one. Number one, HUND'S rule. Let me do it this way. Number one, AUFBAU principle. Sorry about the interruption, senior. Now let's continue. AUFBAU principle. Now, in all the principles, among the principles that we use in writing quantum electron configuration, this one is the most important. So make sure you take it very seriously. AUFBAU principle it says that, I'm sorry about that interruption, senior. OFBAU principles. See, of all the principles used in writing the quantum electron configuration of atoms of elements, the OFBAU principle is the most important one. This one is the most important of the three rules. So it states that electrons in an atom, electrons occupy subshells. It says that electrons occupy subshells in an atom. You understand? From the lowest to the highest energy level. So that means they occupy subshells in an atom in ascending order of energy. Let's now look at subshells. Now, the main shells of atoms, the main shells in an atom are also called main energy level. Are you getting what I'm saying, senior? The main shells in an atom are also called main energy levels. And the subshells in an atom, as in the subshells in these main shells, are also called sub-energy levels. Take note of all these terminologies. They're also called what? Sub-energy levels. So the main shells in an atom are also called main energy levels, and the subshells are also called what? Sub-energy level. So let's go ahead and get the subshells in each main shell. Now, excuse me, sorry about that. Took too long. Now, let me show you this. Now, shell 1. The first main shell in an atom is called shell 1. Let me fill it from the bottom here. The first main shell in an atom is called what? Shell 1. Now, shell 1 has one subshell, one S subshell. Are you getting what I'm saying? Let me start again. The first main shell in an atom is called shell 1. N is equal to 1. That shell has one subshell, which is called the 1S subshell. 1S subshell. The second shell is called shell 2. It has two subshells, 2S and 2P. The third shell is called shell 3. The third main shell is called shell 3. It has three subshells, 3S, 3P, and what? 3D. Let's try and keep that separate as possible. Then the fourth shell is called shell 4. It has four subshells, 4S, 4P, 4D, and 4F. You understand? Shell 5 also has 5 subshells, 5S, 5P, 5D, 5F, and so on. So let's now see how electrons occupy these subshells in ascending order of energy. Now, the first shell we said has what? One subshell called 1S subshell. The second shell has how many? The second shell called shell 2. Let's say N is the shell number. And all of these here represent subshells. The second shell has two subshells, the 2S and 2P. The third shell has three subshells, 3S, 3P, 3D, 3S, 3P, and 3D. The fourth shell has four subshells, 4S, 4P, 4D, 4F. I think that's enough for our level. Let's see how electrons occupy these subshells in order of increasing energy. Electrons occupy these subshells like this. Can you see my line? Look at the arrows. Use your ruler for yours. Can you see? Electrons occupy these subshells in this order. They occupy these subshells in this order. So if I'm to write the OFBAU order now, that means according to OFBAU, the electrons in an atom we first occupy the what? The 1s subshell. The first subshell they will occupy is the what? 1s subshell. Let me try and write that in another color. After occupying the 1s subshell, they will go occupy the 2s subshell. I hope you can see the way I'm following the lines. I'm going 1s subshell, then 2s subshell. You understand what I'm saying? Then 2p. Then what? 2p, then 3s. Can you see my hand? 2p, then what? 3s. In that order. So they occupy the 1s subshell, 2s subshell, 2p subshell, 3s subshell, 3p subshell. After the 3p, they occupy the what? The 4s. Can you see? After the 3p here, they occupy the 4x next. So after occupying or after filling the 3p subshell, they now go and fill the 4s subshell. After the 4s subshell comes what? After the 4s subshell, they now fill the what? 3d. Can you see in that order? Just go from the beginning of the line to the end, come back to the beginning here to the end, come back again to the beginning to the end, come back again and start here. You understand? On and on like that, in that order. That's how electrons occupy subshells. So after the 4s, they will occupy the what? 3d. After the 4s, they occupy the 3d. Let me write that list again. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. You understand? And so on. After 3d, they now occupy. After 3d, they now go occupy the what? 4p. After 3d comes 4p. Just in this order. Starting from here to 3. In that order. So take note of the arrangement. That's what's referred to as the ORBITAL principle. So if I were to draw a line here, this line will show increasing what? Increasing what? Energy. So electrons occupy subshells in an atom in increasing order of energy, or in order of increasing energy. So they occupy the ones with the lowest energy first before occupying the ones with the what? Higher energies. So that's the ORBITAL principle. Then number 2. Let's go to the second one. Number 2. The second one is called, let me use the HUND'S rule. We can call it HUND'S rule simply, or if you like a lot of grammar, you can say HUND'S rule of maximum multiplicity. Some people don't like when there's no big grammar in something. So if you like big grammar, you can call it HUND'S rule of maximum multiplicity. But for people like us who don't really like too much grammar, HUND'S rule is okay. So let's go. HUND'S rule states that electrons, this will bring us to orbitals. Electrons in the same orbital. Electrons in the same subshell, Electrons in the same subshell. Electrons in the same subshell occupy the orbitals. Occupy the orbitals singly first. They occupy the orbitals singly first before pairing takes place. They occupy the orbitals singly first before pairing what takes place. So electrons in the same subshell occupy the orbitals singly first before pairing takes place. Let me show you something very important. Now, we have shells and subshells. The subshells too, or subenergy levels, also have orbitals. The subshells also have what? Orbitals. So let's go ahead and see their orbitals. Any S subshell has one orbital that can take how many electrons? Any S subshell has one orbital that can take maximum of 2 electrons. 2 electrons. One of them spinning upwards, the other spinning downwards like that. Then any piece of shell has 3 orbitals. Any piece of shell has 3 orbitals. 1, 2, 3. 3 orbitals that can take a maximum of 6 electrons. 1, 2, 3, 4, 5, 6. Can you see? That's exactly what we mean by HUND'S rule. You can see that I filled it singly first before doing pairing. I did not fill it like this. 1, 2, 3, 4, 5, 6. I didn't fill it like that. I went singly first. 1, 2, 3 before doing the pairing. That's how electrons occupy orbitals in the same subshell, and that's the HUND'S rule right there. So let's go to the next subshell. SPD. Any D subshell has 5 orbitals. 1, 2, 3, 4, 5. So 5 orbitals. That means the maximum number of electrons it can take is what? 10. Can you see? Singly first. Electrons occupy the orbitals singly first before pairing takes place. So let's go to the next orbital. The next subshell. Any F subshell, we have 7 orbitals. 7 orbitals. And can take a maximum of 14 electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So any F subshell can take a maximum of what? 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Never mind that my marks are spilling into another orbital. It doesn't happen like that in real life. So those are subshells and their orbitals, and you have seen how we make use of the HUND'S rule. What this means is very simple. It means that if you are writing, say for example you want to write 3p4 and you want the electrons to be arranged into their respective orbitals, you will go 1, 2, 3, 4. You understand? This will be the correct thing. You can't do it like this. You're not supposed to say 1, 2, 3, 4. This will be wrong. Is that clear what I'm saying, Senior? This will be wrong. So you do it singly first before carrying out the pairing. I think the last one will come in 4 electrons. So, knowing this, we are good to go. We can write. Let's now write the quantum electron configuration. Let's write the quantum electron configuration of the first 20 elements. Quantum electron configuration of the atoms of the first 20 of the atoms of the first 20 elements. This is going to be interesting. Well, I'll try and be fast. So let's go. Atomic number. Let's do atomic number. Then quantum configuration. Atomic number, then quantum electron. Let's continue with our table. Sorry about that. Now, number 1 here should be what? Hydrogen. Number 1 should be hydrogen. Let me just write the symbol. Hydrogen has okay, let's write the shell configuration first. The shell configuration of hydrogen is 1. It has 1 electron. That electron will be in the 1s subshell. You understand? We start filling the subshell starting from the lowest one. So we are supposed to fill the 1s subshell first. You understand? And any S subshell has just 1 orbital. So that means our 1s subshell, we only have that means our 1s subshell, we only have one box. It will only have one box, and the 1s hydrogen has one electron and its shell configuration is 1. So that single electron will be filled into the 1s subshell, because our rule says we should start filling electrons into subshells starting from the ones with the lowest energy. So we fill the 1s first before 2s, 2p, and so on. So that single electron in hydrogen will be filled into the 1s subshell. The 1s subshell has just one orbital that can take 2 electrons, but here we have only 1 electron. So this will be the quantum electron configuration of hydrogen. Let's go to helium. The diagrams are not compulsory. I'm just going to maybe explain more. Let's go to helium. Helium is the second element and it has 2 electrons. Its shell configuration is 2. So those 2 electrons will be filled into the 1s subshell first. The 1s subshell has 1 orbital. Any s subshell has 1 orbital. So that orbital can take a maximum of 2 electrons. So the 2 electrons will be written into the 1s subshell. This is the quantum electron configuration of helium. Let's go on. It will be somehow at the beginning, but don't worry. The more we feel it, the better you will understand the arrangement. Hydrogen, helium, lithium. The third element is lithium. Its shell configuration is 2, 1. But its quantum configuration will be 1s2 and what? 2s1. This is very simple. We have 3 electrons to fill into subshells. Our rule says we should fill in order of increasing energy. That we should fill the 1s subshell first, before the 2s, before the 2p, before the 3s, and so on like that, according to the AUFBAU principle. So we go ahead and fill the 1s subshell first. Now, the 1s subshell has 1 orbital because any s subshell has what? Just 1 orbital, 1s. So, and that orbital can take only 2 electrons. So we fill the first 2 electrons into that 1s subshell. You understand? And then we go to the next subshell to fill the third electron. So this is how everything looks in picture. But this is the quantum electron configuration of lithium. 1s2, 2s1. So let's go on. Number 4, hydrogen, helium, lithium, beryllium is the 4th element. Its quantum configuration is 2, 2. The first 2 electrons will go into the 1s subshell. That subshell has just 1 orbital, which is the s orbital, that can take 2 electrons. So the 2 electrons will be kept inside. The first 2 electrons will be kept inside that subshell. After filling the 1s subshell, the next subshell to fill is the 2s subshell. The 2s subshell too is an s subshell which has just 1 orbital. So it will just have 1 box. So the diagram looks like this. It will just have 1 box, and that box will only take 2 electrons. So the quantum electron configuration of beryllium is 1s2, 2s2. We will gain momentum. It will look somehow at the beginning, but as we move on, it will be clear. You will get to a place where you will say, let me pause this video and try. That means that there will be 2 electrons here and 2 here. So we say the quantum electron configuration of beryllium is, 1s2, 2s2. Let's go on real fast. Number 5, boron. Boron shell configuration is 2, 3. The quantum configuration will be 1s2, 2s2, 2s2, 1s2, 2s2, 2p1. 1s2, 2s2, 2p1. So I hope you understand now. After filling the after filling up the 1s of shell, I'll go put another 2 in the 2s of shell, then the last one will be in the 2p of shell. Let's now see how the arrangement looks in picture. So 1s of shell, the 1s of shell is right here, 1s of shell. The 2s of shell is next to it, 2s of shell, and then the 2p of shell is right here. Any piece of shell has 3 orbitals, so this is going to have 3 boxes that can take a maximum of 6 electrons, but after filling 1, 2, 3, 4, there'll be only 1 left. So I just put that one right there. This is the quantum electron configuration of boron. Let's go to beryllium. It should be taking shape in your mind now. Let's go to carbon, not beryllium. Let's go to carbon. Carbon is number 6. Carbon is what? Number 6. Okay, I've not been writing in full. For carbon, let's just write C. So the shell configuration of the atom of the electrons in an atom of carbon is 2, 4. So 1s2, 2, 1s2, 2s what? 2, and what? 2p. 1s2, 2s2, and 2p2. 2p2. Is that clear? So I'll go ahead, fill the first subshell, 1s, go to the second subshell, 2s, and after filling the second subshell, I still have 2 more electrons to fill into subshells, but I will now go into the 2p subshell. You understand? Next. So in picture, it will all look like this. 1s, it will look like this. 2s, and then the third one will look like this, 2p. Actually, the 2p subshell has 3 orbitals, but on getting to the 2p subshell, I don't have up to 6 electrons left. First 2 here, 2s2, 1s2, 2s2. I hope you got that. Then I will have 2p2. Can you see I did not do 2p2 like this? You understand? According to HUND'S rule, the electrons will occupy the subshell singly first before pairing takes place. The electrons will occupy the subshells singly first before pairing takes place. So take note of them. So the quantum electron configuration of carbon is what? 1s2, 2s2, 2p2. Take note. Let's go to nitrogen, number 7. Nitrogen. I prefer this light green. Nitrogen. And the shell electron configuration of nitrogen will be 2, 5. So 2, 5, I'll start filling my subshells. 1s2, 2s2, then 2p3. I think that's complete. 7 electrons. So in picture, it will look like this. 1s2, 2s what? 2, and then what? 2p what? 3. So this is how everything looks in picture. 2p3, 2p3, 1s2, 2s2, 2p3 singly before pairing takes place. So it is when I get to an atom where I have enough electrons to go singly the first row and then come back and fill more, that pairing will start. But for nitrogen, each one will still contain only 1 electron. Oxygen next, number 8. Oxygen next. Oxygen has 8 electrons, 2, 6. So the quantum electron configuration will be 1s2, 2s2. 1s2, 2s2. Let me try and write 1. 1s2, 2s2, and 2p4. So I go from subshell to subshell. The 1s subshell first with 1 orbital only, s orbital. Then 2s subshell with 1 orbital only, s orbital, 2s orbital, which can only take 2 electrons. Then I'll go to the 2p subshell. Although that one has 3 orbitals, you understand, that can take 6 electrons. Since I don't have up to 6, I'll just fill in what I have. So let's draw the picture. 1s orbital, 2 electrons, 2s orbital, 2 electrons, then 2p orbital, 2p, 2s, 2p, 2s. So let's fill 1s2, 2s2, then the p, these 2 pieces of shell. Any piece of shell has 3 orbitals and can take a maximum of 6 electrons altogether. But for this subshell, we don't have more than 4 electrons to fill into it. So I'll go 1, 2, 3, then 4. I hope you can see that. So next is what? Next is fluorine, F. That's 9 electrons in its atom. 1s2, 2s2, 2p5. So that's the quantum electron configuration of fluorine. 1s, 2s, and what? 2p. Let's try and make it beautiful. So 2 electrons here, 2 electrons here, then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's how the electrons occupy the orbitals in the subshell. Let's label our subshells. 1s, 2s, 2p. Let's go on. Let's go on. Number 10. Nitrogen. The shell configuration of nitrogen. An atom of nitrogen has 10 electrons. The shell configuration is 2. Sorry, I said 10 electrons. Neon, not nitrogen. An atom of neon has 10 electrons. So its shell configuration is 2, 8. The first subshell to be filled is the 1s subshell. It will take 2 electrons in its s orbital. Then the 2s subshell. Then the 2p subshell, 2p6. Then, okay, that's all. That's all. We filled all the 10 electrons. 1s2, 2s2, and 2p6. So, in picture, it will look like this. 1s2, 2s2, then 2p what? 6. 1s2, 2s2, and 2p6. 1s2, 2s2, 2p6. 1, 2, 3, 4, 5, 6. That's the quantum electron configuration of neon. Let's go to the next element. Next element is what? Sodium. That's element number 11. Sodium is Na. An atom of sodium has 11 electrons in its shells. So its quantum configuration will be 1s2, 2s2. I'll just take the subshells one after the other and fill them completely before I go to the next one. So if you check your arrangement, like I said at the beginning of the topic, if you check your arrangement, I'm supposed to fill the 1s, then go to the 2s, then 2p, 3s, 3p, 4s, on and on like that. So when I get to a subshell, I will now determine whether the subshell has just a single orbital or whether it has 3 or whether it has 5. Any piece of shell has what? 3 orbitals and can take a maximum of 6 electrons. So that's how I have 2p6 here. Let's draw what the picture looks like inside the atom. 1s subshell, 2s subshell, 2p subshell. One S subshell, 2s subshell, 2p subshell. Then Okay, let me fill this completely first. They are not supposed to touch each other. Lastly, 3s soft shell. With just one electron. So that's what the picture looks like inside the atom. Meaning 1s2, you understand, 2s2, 2p6, and what, 3s1. That's how the 11 electrons are arranged in the orbitals of an atom of sodium. Let's go to the next element. Next element is number 12, magnesium. Now, an atom of magnesium has 12 electrons. So its shell configuration is 2, 8, 2. I think we did this before. So that should not be difficult for you. The quantum electron configuration will be 1s2, 2s2. After filling the 1s and 2s subshells, electrons will then fill the 2p subshell. After completely filling up that, they'll go to the 3s subshell. So that's the quantum electron configuration of magnesium. So let me make that straight. Okay, that's good enough. So the picture looks like this: 1s, 2s, then what, 2p, then what, 3s. So 1s, 2s, 2p subshell, then the 3s subshell. Now don't forget, any p subshell has 3 orbitals. So the 2p subshell will have 3 orbitals: 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6, then 3s2. That's how electrons are arranged in the subshells and orbitals of magnesium. Okay, let's go. Magnesium, number 13, is what? Aluminium. An atom of aluminium has 13 electrons in its shell. So its configuration is 1s2. Quantum configuration is 1s2, 2s2, 2p6, 3s2, 3p1. You can see now we are getting to fill more and more subshells. After filling all of these subshells, you still have an extra electron left that must be kept in the next available subshell. So let's draw a picture of what everything looks like inside the atom. 1s, I'm just going to make it shorter now. 2s, 2p, 3s, then what, 3p. Can you see? I make it big when it has more orbitals, and small when it just has and small when it just has a single orbital. 1s2, 2s2, 2p6, 3s2, 3p, 3p what? 3p1. So although this 3p subshell can take a maximum of 6 electrons, we don't have up to 6 electrons left after filling all the previous subshells. We just have 1 electron left. I'm getting to the 3p subshell here. There will be just 1 electron left to occupy it. So that electron will occupy the px subshell. This is the px, py, and pz orbitals. So that electron will occupy the px orbital. This subshell has 3 orbitals in it: 3px, 3p1, 3pz. Just like here too, there are 2px, 2py, and 2pz orbitals inside the p subshell. Are you getting the terminologies? A subshell also has orbitals. So take note of that. Next is what? Next is element number 14. That's what? Silicon. Silicon has 14 electrons. We said it shell electron configuration is 284. So quantum electron configuration for it will be 1s2, 2s2, 2p6, 3s2, 3p2. I think that's 14. Yeah, 14 electrons. So let's draw what the picture looks like in an atom of the element. Let's draw what the picture looks like in an atom of the element. I'm sorry. So 1s2, 2s2, 2p. Okay, let me correct that. 2p should be 3 orbitals, then 3s, then 3p. So the electrons will take, their places starting from the lowest one. Okay, that was an error. Singly first, according to HUND'S rule, before pairing takes place, and they should not touch each other. So 3s2 and 3p2. I think that's 3s2, 3p2. So this is the quantum electron configuration of an atom of silicon. That means that's how the electrons of a silicon atom are arranged in its subshells and orbitals. So 15 is what? Phosphorus. 15 is phosphorus. Phosphorus is okay, let me just use P. 15 is phosphorus. P. That's 285. That's 1s2, 2s2. I'm going to be faster now. 2p6, 3s2, 3p3. So in picture, it looks like this in the atom. 1s2 looks like this in the atom. 1s2, 2s2, 1s2, 2s2, 2p6, 3s2, and what? 3p3. So that's what. Let's now fill electrons into it. 1s2, 2s2, 2p6, 2p6, 3p3. Am I getting that right? Okay, 3p3. So 1, 2, let's draw it straight. 3p3. So that's what that's how electrons are arranged in an atom of phosphorus. Next is what? Sulfur. 16 sulfur. An atom of sulfur has 16 electrons. That's what? 2, 8, 6. So its quantum electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. So that's a configuration. That's the quantum electron configuration of sulfur. In picture, it will look like this: 1s, 2 electrons, 2s, 2 electrons, 3s, 2p, 1s, 2s, 2p, 3s, and what? 3p. So any p subshell has what? 3 orbitals, and any s subshell has 1 orbital. So 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6, 3s2, then 3p4. 1, 2, 3, 4. Okay, that's it for sulfur. Let's go to number 17, chlorine Cl. That's 287. The shell electron configuration is 287. Then the shell electron configuration is 287. 287, that's 1s2, 2s2, 2p what? 2p6, 3s2, and 3p5. How we got that? So that's how. In picture, it will be 1s2, 2s2, 2p6, 3s2, and 3p. So let's put electrons there. 1s2, 1s2, 2s2, 2p6, 2p6, 3s2, 3p5. Three p5, 1, 2, 3, 4, 5. So five, I'm sorry. So that's all. Just 1, 2, 3, 4, 5. 3p5. So that's how the electrons in an atom of chlorine are arranged. Let's go on. We should be able to finish quickly now. 18 now. 18 is argon. That's 288, 1s2, 2s2, 2p6, 3s2, 3p, 3s2, 3p6. So that's 18. So you know what it should look like in picture. You draw it yourself. I'm going to leave that for you. 19 is what? Potassium 2881. So this is where, let me try and draw the argon. 1s2, 2s2, 2p6, 3s2, 3p, what? 6, 1, 2, 1, 2. So electrons now. Well, let's write the names first. 1s2, 2s, 2p, 3s, and 3p. So the electrons are 1s2, 2s2, 2p6, 3s2, and what? Did I feel that well? Should have been 1, 2, 3, 4, 5, 6. Okay, that's right. 3p6. Potassium will be 1s2, 2s2, 2p6, 3s2, 3s2, I'm sorry, 3p6, and what? 4s1. 3p6 and what? 3p what? 6 and 4s1. You can now see our exception. You understand? Our exception. The exception I was talking about is right here. Because we get to fill the 4s of shell before filling the 3ds of shell. And unfortunately, the 4s of shell is part of the 4th shell and not part of the 3rd shell. But when arranging subshells using the ORBITAL principle. The 4s subshell comes before the 3d. So we have to fill electrons into it first. So that's the reason for the exception. That's the reason we write 2881 instead of simply writing 289. You understand? Because the 9 electrons don't all go into the third subshell. Only 8 goes into the third subshell. The remaining one goes into the 4s subshell. Only 8 go into the third shell. The remaining one goes into the fourth shell and into the 4s subshell. So let's quickly do this. Diagram. I should have stopped drawing, but let me just be nice to you. I should have stopped drawing. Let me just be nice to you. 1s. That was too small. 1s, 2s, 2p, 3s, 3p. That's too big. 3p. Then what? 4s. I think that should have 4s, 3p, 3s, 2p, 2s. Each one with its electrons. 1, 2, 1s2, 2s2. I forgot to break this into orbitals. 1, 2, 1, 2. Okay. 2p, it should be 6, but I feel singly before pairing takes place. 3s2, 3p, 6. 1, 2, 3, 4, 5, 6. Then 4s1. You understand? That's how that's how electrons occupy the shells, subshells, and orbitals in an atom of potassium. So, lastly, calcium, number 20. Element number 20, calcium. Okay. Calcium. Calcium is Ca. Its shell electron configuration is 2882. And its quantum electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So I think I got the 10. Yeah, that's complete. So we'll draw a diagram for it too. Let me go further down a bit. So 1s, 2s, 2p, 3s. Let's try and manage our space now. 3s, 3p, and what? 4s. So 3s, 3p, and 4s. So each of the p subshells has 3 orbitals. So electrons will now occupy the orbitals and subshells in this way. 1, 2, 3, 4, 5, 6, 2p6, 3s2, 3p6, and 4s2. So that's all about the quantum electron configuration of the atoms of the first 20 elements. That's all about it for now.